Okay, so in our output that we looked at previously, we generated the implied volatility consistent with particular parameter inputs. So we're getting the information out in this format. We could tidy that up a little bit, I suppose. So let's close that down. And I'll make some changes here to the code and then run again. So I've put in a few more comments and end line instructions. So let's run again and see what comes up. So it should be slightly better formatted, and we get some output then over here, and you can see we get the beta output and then the implied volatility when k is equal to 130 and t is equal to 0.1 years, so it would be 0.180515, and the at the money option 30 days. So again, it's the implied volatility. I should have probably said again, the implied volatility at the money option with 30 days. So let's run one more time and just get that clearer. So the implied volatility at the money with 30-day maturity would be 0.178107. So can I verify those results? Well, I could take a look in Excel. Okay, and if we use the spot price, so let's get these values again. The values we're comparing against are, well, it looks as if, okay, so for the implied volatility when k is equal to 130 and t is equal to 0.1 years is 0.180515, and we get something similar here, 0.18052, so that's where the exercise is 130 and the time period is equal to 0.1. So some results that are consistent, but then when we run the implied volatility for the at the money option for 30 days, we get different results. Right, so the basis of this was that we had taken these implied volatility estimates where we had written A5 here multiplied by the product of k by t, the exercise by the time period. We had estimated using Linest coefficients for the constant A1, A2 up to A5. If I put in if we take a 30-day period, that's equivalent to 30 divided by 365 days when expressed in terms of a year. That would be 0.08219. And if we take if we took the at the money option, then the exercise would have been equal to the spot, and we saw before the spot we had incorporated in as 129.14. When we run those estimates here, we find that the implied volatility, so just to verify that, when we take these coefficients, use this relationship, work out the implied volatility, we got a figure of 0.18099. When we look at the output here for the at the money option at 30 days, it's giving 178,107. So let's go back and verify our results. Okay, and the issue is we are getting some difference, and the reason here is, well, the first value, when we estimate implied volatility using those betas, for the at the money option 129.14, yeah, that's a double, but this one is represented as an integer. So instead of writing 30 divided by 365, we could do what we had done with take the value as a decimal. This value is 0.8219. So let's take that value and put in. So let's copy, go back into Visual Studio for a moment, and we'll paste that value in, and then come back. Okay, and it's now coming up as a double, so let's run that. See what output we get, and the output now appears. And so for the implied volatility at the money option with 30-day maturity 0.180995, let's compare with Excel for a moment. Right, Excel. With Excel, the value that we have here is the at the money option. At the money option is 18099, so 18099. And for the value where the implied volatility, the exercise is 130, exercise equal to 130, and the time period equal to 0.1 years, we get 0.18052, which is the same value here. Okay, so the results that we're getting from the C++ project is consistent with the data table that we have here. The way we generated the data table would just be very simply, we take a data table, we go to Data tab, What If Analysis, Data Table. The row here is the time period, and the column here is the exercise. And when we run, the value fills up, right? And you can see the values are consistent with what we had before. And if we take a separate parallel table, then we can generate this volatility surface. So the data that I have here can be used. Data here can be used to generate this volatility surface. And there's not a lot of definition here because the time period involved is relatively limited, but also the range of exercises is just going from 124 to 136. So we don't get the very quadratic curved type shape typically associated with a surface, but it's a surface nonetheless. So all in all, we find that the deterministic volatility function we've set up in Excel, but we've also set up in C++, and in both instances we're getting the same results, and virtually the same results for the beta coefficients or for the parameter coefficients for the deterministic volatility function. Okay, so on the YouTube portal, I will leave a link to the modules here, the implied volatility and the bisection estimation for the put option. So the bisection technique that's used to generate the implied volatility. Otherwise, it's relatively straightforward to follow.